Great. So what we're doing is the Innovative Technology panel, as we have done in a few of our previous meetings. And this time we are asking the panelists to stick to a very strict 5 minutes. You can see the clock there. Lloyd will be standing up and down if it goes over the 5 minutes. But we're asking each of the presenters to address 4 very straightforward questions. The first one is to pick out an innovative technology, probably from your company or in your area, is the intent here. And something that's innovative that you're working on, and just describe it very briefly. And then why is it disruptive? You know, how could it change what's going on in the marketplace? And then the third one is, what does it do for the end user? You know, why should people care about it? And then the fourth question is, what could you use from buyers, partners, members of this user forum, government bodies and that, to bring the technology to market sooner or to make it better? And with that, we don't have a particular order here. How about if we start with Panasas, just because it's the first file I have on the list here. Yeah, if it's easier, you can come up and use this. And then the top one will give you forward, backwards, and a laser.
Oh, great. So our innovation is simplicity. For 10 years now, Panasas, high performance parallel file system, has focused on making its solution as simple and as reliable as possible. Been heads down on that for a long time. And that's in contrast to a lot of the other solutions in the market for high performance computing, which are known to be very performant, but are also have a reputation for being very complex. So we sponsored a survey with Steve Conway and Hyperion recently to see how what the effects and benefits are of simplified management with high performance computing organizations. And this is some of the slides is a preview of the report, which is coming out soon. And one of the slides is that we surveyed what was the top purchase criteria for high performance storage and its performance and price. No big surprise there. And then farther down the line is things that would indicate simplicity, like number and skill set of staff required, recovery, resiliency, software support. So the initial look at this is like, wow, simplicity is not really a big deal for high performance computing. And that kind of makes sense. Everyone's really focused on performance and price performance. And so this kind of initially was kind of disappointing to see for someone that's been focusing on simplicity for so long. But then some other questions arose, like what is the most challenging aspect or the biggest pain points of running your HPC storage infrastructure? And it was, this came up, recruiting and training. Remember that was a very low thing on the previous slide. Tuning, installation time and cost. So these were the biggest pain points. So the takeaway that I got from this is that everyone is so focused in this space on performance, price performance, and they accept some of the downsides. These are compromises that maybe the marketplace doesn't realize that they could potentially get both performance and simplicity, reliability, not rely on experts to run these complex systems. What would it do for the end user? Here's some more results of the survey. 78% report storage-related issues negatively impacting the productivity of the site. 60% require more than one dedicated person to manage their storage. 32% of sites using Lustre, BGFS, and Spectrum Scale spend more than $300,000 annually on storage management staffing. And then 25% of sites estimate a day of downtime costs them more than $100,000. So the message I wanted to get across is that we have this simple solution that mitigates a lot of those problems, but we also have a very high performance solution now. We just introduced at Supercomputing last year our new COTS-based ActiveStore Ultra that's based on the Supermicro hardware. And in addition to providing very economic benefits of a COTS-based architecture, here's the performance of this new system compared to the other parallel file systems out there. So the bottom line is that we can provide both performance and simplicity. That's the innovation that we provide. And how you can help getting this out there is to actually to consider that as you look at your high performance storage systems, and you want performance, you want price performance, but don't give up on demanding reliable systems, easy to manage systems. It's harder and harder to get talented people to run these systems. The battle for talent is affecting this area too. And moving forward, simplicity is going to be, I think, a bigger part of the buying criteria as running these complex systems is becoming more and more difficult moving forward. And with that, I'll end my talk. Okay.
Next we'll go with Cray, particular order, just microphone.
All right, thank you.
Take you forward, backwards, and a laser.
All right. Thank you. So a lot of things to choose from our perspective, right? A lot of new technologies coming out. You heard from our CTO yesterday, Steve Scott. He was talking about Slingshot and a lot of the new interconnects. Got a lot of new CPUs coming out, so I decided that I would stay with the storage side, right? Because what we see is, what we heard all morning was data, right? We've got more data, we need more data. And this becomes very expensive, and it can also be very limiting since the interconnects and the CPUs are now processing at a much higher speed. So at the very top, you've got SSDs, right? And they've kind of replaced the SAS drives in node local storage. We start seeing them, saw them a little bit more in storage for the whole clusters, right? But as we move into 2020, the disruptive shift is that we see that the price of SSDs on a per terabyte is actually past SAS, right? But still continues to approach nearline SAS or SATA drives, right? So there's still a place on the low end, right, for hard drives, but SSDs have become more part of the storage ecosystem, right? Because we've got faster interconnects that are supplying data, we've got much bigger data requirements, and we've kind of shifted, and I think you heard a little bit about this yesterday, we've shifted a little bit from hard drives and tape, right, to more of SSDs and hard drives, right, where hard drives are now becoming more the standard for the archived data, right, or the data that's going to be persistent over a longer period of time, right. So just to give you an example, right, the Cray storage, we've got flash arrays and disk arrays, right, so we're making more use of standard SSDs, right, in flash arrays that will be network connected, and also disk arrays, right, for the larger capacity storage. And what we're also seeing, and I think you saw in Steve Scott's presentation, is we're moving away from storage area networks, right? Things become more direct connected. You don't have to use LNet routers or gateways to go from the high-speed interconnect, right, which is where the compute nodes live, out to the storage or even out to the user, right? And even more important, as we go into areas like AI and machine learning, right, there's staged data, right? So you end up with this tiered workflow when it comes to storage. So the first job completes, it sends the data off, right? So it'll do some pre-processing, it can put it into flash, and then the data assimilation job starts, and it pulls it from flash. So there's more a staged area. Right? what can we do to further this type of technology? And it really comes down to workflow automation, right? Being able to have things directly archived from SSDs, right? From that much faster but more expensive space into the hard drive area, right? So Cray is spending a lot of time over the next couple of years developing more of these capabilities and automating a lot of it with policy-driven software. And just to mention some of the bigger systems that we're going to be building, right? So NERSC Perlmutter, right? This one was all flash, right? It's 30 petabytes of complete flash with 4 terabytes per second, right? Then there's Oak Ridge, right, our frontier system. This will have greater than 10 terabytes per second with an exabyte of raw capacity. And then, of course, last but not least, Argonne, right, at 200 petabytes and a terabyte per second. And that will actually be deployed in the first half of next year. That's it.
Well, good morning. Thank you very much for the opportunity to be here. IBM is co-sponsoring with NVIDIA. I want to quickly acknowledge two people. Fred Allman is the Director of Worldwide Supercomputing for NVIDIA, who's here with us today, and Marianne Picone, who's our client executive for all the Coral accounts and other DOE accounts from IBM. What I chose to talk about is machine learning accelerators, which are really productivity and optimization tools for data scientists and other users. So what's the problem? Well, data scientists have very time-intensive and skill-intensive work. Their model experimentation takes lots of time. Experimenting with hyperparameters before they can even run the models takes a lot of time. Then they have to wait on execution and do lots of iterations to train their models. At the same time, domain scientists and other users wish they could do some of that work and maybe don't have the deep skill sets. So there's a lot of room for productivity improvement here. So what I'm going to talk about mostly centers around the red circle here, around hyperparameters, which is the third stage of a machine learning workflow. You can see that before you even do the model training, you have to search for and optimize hyperparameters to even start doing all the iterations and hyperparameter tuning to finally come up with the best models. So what is a hyperparameter? It's a basically they're configuration settings for neural networks that optimize the results and make them faster. A couple examples would be learning rate would be one. Every layer of a neural network has a set of weights and biases which are tuned to come up with faster, better results. And learning rates need to be tweaked to come up with optimal models that converge. Another example would be iterations or epochs. How many times you run a model to get the result? And there's a few to hundreds of parameters that could be tuned for every neural network. The process of setting hyperparameters requires a lot of expertise and extensive trial and error. So wouldn't it be cool if there's a way to automate some of this work? Well, actually, IBM has something called the auto hyperparameter tuning in one of our software products, which actually is based on grabbing some data from the sample data from the training set, and then doing a bunch of sample jobs, running and finding the best parameters, hyperparameters for the data scientists to use to build their models, and it's based on 4 different search algorithms that we use for the HPO or hyperparameter optimization. This is what it looks like in practice. The first screen on the top is, for a particular cafe job, going out and finding out asking for some hyperparameter settings and recommendations. At the bottom, you can see it comes back with a decay rate and base learning rate using those different algorithms. And in addition to doing the hyperparameter selection and tuning, we also have visualization tools, so the scientists can actually monitor and analyze the neural network jobs to save time and get better performance, more optimal results. A couple other examples from IBM. This also came from IBM Research, like many of our other software products. Is we have a Bayesian optimization accelerator, which we'll be announcing next quarter. These are for jobs doing large multidimensional design space searches to identify optimal product points. I know it's a big mouthful there. It's actually been successfully deployed in a lot of industries already. Something we'll have available next quarter. And by the way, all the software tools I'm talking about actually, even though they were developed for the IBM Power Architecture using NVIDIA technology and other partner technologies, they are in fact platform hardware agnostic, so they could be used on x86 as well. Another last example here is, wouldn't it be cool if people who aren't data scientists could actually do some machine vision? So we have an optimizer called Power AI Vision, which lets novice users actually do data labeling, build models, and deploy for inference using images and video. How does that make this available? Well, these are all different software products that are part of our machine learning accelerator library, again, which runs primarily on IBM NVIDIA servers, but also on x86. One way we deliver it is people who want a little, like kind of a ramp-on kit for Summit or Sierra could buy a mini Coral Summit kit from us with the HPC stack and the hardware from IBM and NVIDIA that they use at Summit and Sierra with these training models. We usually deliver this with a workshop. So thank you for your time. We talked about how we advance data scientists and other user productivity using machine learning accelerators.
You just hand that to the next speaker. Next will be AMD. Top one goes forward, reverse, and then up laser time. Perfect.
All right.
These are all loaded. Yep.
All right. Thanks, everybody. So I'm Andy Parma. I'm the segment leader for the HPC business at AMD, and I wanted to just spend a couple minutes talking about the AMD Infinity architecture here this morning. So it's going to start with a little bit of a history lesson, kind of how we got to where we're at today, but also going to talk about where Infinity architecture is going in the future, and then wanted to, like I said, when we get to the conclusion, open it up to thoughts from you guys. Like I say, try to find me or some of my peers after the show. We've got some ideas on where Infinity architecture is going, but obviously want to take the community feedback into account there for how the roadmap evolves over time. So like I said, I kind of mentioned that we're going to start with where we've been. So in 2017, AMD introduced the first generation of AMD EPYC processors, which used the first generation of the Infinity Fabric interconnect. So this was a interconnect that connected 4 CPU die within each of our processors within the package, but also the same fabric went socket to socket, so connecting the multiple processors in our 2-piece server. So this is a coherent fabric, high bandwidth, low latency, but one of the other things that's unique about it is it's muxed with PCI Express lanes. So some of our customers are building servers with first and second generation EPYC processors where these Infinity Fabric lanes can be used for extra PCI Express lanes to give extreme expandability from an I/O standpoint. So that's kind of where we started. You know, the coherency within the CPU package and then socket to socket. Where we went to next in 2018 was we expanded that into our GPU connectivity. So we introduced a product line that we call MI50 late last year, and it was had a coherent link or a high-speed link between the GPUs that allows the sharing of the memory. So each of these GPUs that's pictured here has the high bandwidth memory on the package, and with the Infinity Fabric architecture interconnected them that allows that memory to be shared amongst the 4 GPUs. And then the most recent extension that we made to Infinity Fabric was last month. We introduced the second generation of the AMD EPYC processors. And so with the advances that we made there by going to what we call a hybrid multi-die design, or some people call it a chiplet design, we're able to use these high-performance Infinity Fabric links to connect the CPU and I/O die together, enabling us to have extremely high performance and extremely high throughput. Also, we added PCI Express Gen 4 capability to the second generation of EPYC, so going to a higher performance Infinity Fabric to enable balanced systems to be built with PCI Express Gen 4. So this is kind of how that looks, kind of comparing that first generation in 2017 to the second generation in 2019, and you see that we went from the four die on the left with the Infinity Fabric connecting four identical die to now the optimized architecture with the second gen EPYC, where we've got all of the I/O and memory on a single die, so you have very consistent bandwidth and latency going to all your I/O and memory devices. And then you've got the 8 small CPU die there, which are in the high-performance 7-nanometer process. And again, Infinity Fabric now, with a new implementation with the second-gen Infinity Fabric, connects all of those devices within the processor package. So that's where we're at today. So next innovation that we'll be making, this will be coming to market in 2021, we'll be extending Infinity Fabric to connect CPUs to GPUs. And the first production, or I should say the first publicly announced production version of this is going to be in the Frontier supercomputer. So like I said, we've got Infinity Fabric within the CPU, CPU to CPU, then GPU to GPU today. When we get to the Frontier supercomputer in 2021, that's when you'll extend the Infinity Fabric to connect the CPU to the GPU, enabling, like I say, new levels of coherence in that system. And then, where we go next, this is where, like I say, we're seeking input and direction from the folks here. We've got, obviously, our roadmap and our own plans for where Infinity Fabric goes next, also where C6 and Gen Z and CXL fit into the AMD roadmap. We're active participants in all of those consortia, but like I say, as these multiple coherent technologies fit together in our roadmap and in your roadmaps, like I said, we definitely want to seek your input on where we go next. Thank you so much.
Any questions from quite proud today? Sorry. Okay, great. Thanks.
Good morning. I'm going to put the mic close to me so the sound guy can adjust. I'm going to talk to you about something that truly is innovative and is really going to change the world. As a matter of fact, the song in my head this morning was, no, I won't say it. Yeah, so we all know about U.2. We've all seen M.2, right? All of those are very, very common form factors for us, but there's a brand new form factor that's out there today, and it really is innovative, and it's really going to change the world, and it's not going to be the world as we know it. So, in a little... We also may have seen NF1, but EDSFF is what this brand new form factor is, and I want you guys to know about it. I was really surprised when I went to ICS in Germany, and I'd say EDSFF, and people went, what? And I'm like, you don't know this? So that's why I'm talking about it. So what is EDSFF, and really why do we need a new form factor? Well, we need a new form factor because that 2U24 box you're so used to is not very dense. We can go 1U32 with EDSFF. I can put 32 drives in a 1U box, so I can significantly improve the amount of density that I can have. I can also pack the die, those flash die, really don't fit so great on a 2.5-inch drive form factor. That was meant for hard drives. So why not have a form factor that's really meant for flash? So that's the other reason why we can get so much better storage density. The other great thing about this is thermals. So much better thermals, and I'm going to go into that in just a minute. So much better, higher capacity that we can get on the drives. We're talking about 16 terabyte, 32 terabyte drives, so that you can put a petabyte into 1U box. So that 30 petabytes that he was talking about, that can fit in a rack, not a problem. You don't need racks and racks and racks and racks to get petabytes of data anymore. So what is EDSFF? 15 companies got together to come up with the spec. It is a standard spec across, so it's not proprietary, and it's optimized to do all of the great things that I just talked about. But there are lots of form factors. There's this long, there's a short, there's a long that's kind of wide, there's also a 3-inch. There's all kinds of things with EDSFF, but right now the primary focus is going to be the long and the short. The connector's got 3 different connector types that you're going to hear about, and the best thing to learn about this connector is already ready for PCIe Gen 4 and Gen 5. Your U.2 connector, it'll do Gen 4, but it's not going to do Gen 5, guys. So eventually U.2's got to go away, and EDSF is going to take over the world. So here's the reason why the thermals are so much better. I'm an engineer, okay? So when you design a backplane, that backplane is a big air dam that sits in the front of a server. It blocks all the airflow. You punch as many holes into it as you possibly can to get some air back to the CPUs and the DIMMs. What you do with EDSFF is they take that air dam and they lay it down flat. So now you have connectors that are vertical connectors no wider than the device itself, so the air flows right through the connector, right through the drive. You no longer have that big air dam in the middle or in the front of your server. So that's why you have so much better thermals. Why do you care? Because if I can improve my thermals, I can slow down my fan. If I can slow down my fan, I can take a lot less power. And if I can take a lot less power, then it's going to save you a lot more money. So not only am I going to save you money in that you don't need racks and racks and racks and racks and racks to put petabytes of flash, but I can also save you money in power. So this shows you 55% better airflow loss compared to U.2 to EDSFF. So you can improve that significantly, and that's one of the reasons why this is going to take over the world. So we have products. Supermicro has products for this. This is our 1U. This is the product I designed personally. It's our long product. So EDSFF long, 32 drives, 200 gigabits of Ethernet out the back, 24 DIMMs, all the processing you want with Cascade Lake processors, and of course we're going to come out with the next gen after that. I don't have much time, so I'm going to be quick. This is our JBOF version, so you can have JBOF without processors. Same sort of thing with 32 drives in it. We can do short. This is a much shorter chassis with the EDSFF short version, much shorter than the long. And then we've also taken our big twin, which is a super dense 4 nodes in a 2U, and put 40 drives in it. So you've got 40 drives in front. How can you help? One of the things that's happening, I've heard all this whole conference how hyperscalers are helping with HPC. Well, in this case, they're actually not, because there is one hyperscaler out there that's really driving a very low-dense solution. So how can you help? Go for that 9.5 millimeter long drive. I'm out of time.
Great, thank you very much. Any questions? We're going to save questions for the whole panel at the end.
There we go.
And then this should go forward, backwards, and up.
Great.
Great.
Thank you. Jan Fischer, Red Hat. I'm a global evangelist, and so I'm here rightfully to talk about innovative technologies and whatnot. But instead of talking about many projects that we're involved in today, I'm going to front load this talk a little bit at the risk of never being invited to the innovations panel ever again. I'm going to talk about the elephant in the room, so to speak. Many of you have asked questions in the past, what's going on with the Red Hat acquisition. So I'm going to do that, and then I'm going to get to the core of this panel and discuss the innovations. So in the very bad impersonation of Mark Twain, the reports of my death are greatly exaggerated. Red Hat is still Red Hat, and that is basically what you need to know as our customers and partners, many valuable relations here in the rooms, many people I've known for years. Quick set of facts here. The acquisition has been completed now as of July 9th. IBM has purchased Red Hat for $34 billion, and we will operate as a distinct unit within IBM and will be reported as part of the cloud business unit and cognitive software, business unit within IBM. We'll continue to stay on course with our software innovation, commitment to open source, our development, our product portfolio, et cetera, et cetera, et cetera. So nothing is really changing. The only change that we know internally is one employee of Red Hat has actually gotten an IBM badge, and it's our CEO. Everybody else, we don't have access to IBM systems internally. There is a firewall still in place. So we kind of separated for good reasons, most of which has to do with continue to work with the market partners and global hyperscalers like we have done in the past. And the perception of the work that we're going to have in the next many, many years is really circled around synergy. So it's a synergetic relation where one culture will not overwhelm the other, will just work together. And from customers' perspective, we continue to deliver same set of values and same technology as we've been known for from the open source standpoint. So why did IBM spend $34 billion, which is probably the most valid question, is because we actually share a common objective. We firmly believe, and our leaders are, in the hybrid cloud concept. You can read the slide, but in a nutshell, ability to run your application anywhere on any footprint in any cloud is the vision that Red Hat has maintained for over 5 years now, and we've been developing our entire product portfolio to essentially align around that strategy. From bare metal, which we also consider, by the way, we can argue about that later, part of the hybrid cloud, from bare metal to virtual to private cloud or a public cloud, our platforms, our software platforms, run cohesively across. The part of the openness is in the open cloud is related to the fact that we pull from thousands and hundreds of thousands of projects upstream, and we nurture them into communities, and we produce standard offerings that enterprises and hyperscalers and high performance sites can consume out there. Our portfolio is all open source. We don't have any proprietary pieces in our portfolio. The hybrid part comes from the fact that, as I said, you can run on-prem, you can run in the private cloud, public cloud, with all of the major cloud providers, and all the way out to the edge. And that part of that is the vision around Kubernetes-enabled orchestration software that we called OpenShift. But fundamentally, we kind of separate our hybrid cloud vision into 3 big buckets. We talk about the infrastructure for the hybrid cloud. We talk about hybrid cloud or cloud native development, and then management and automation that comes around that. Why is it important? Because not everyone is interested in the application development part of the cloud native. Most people here in the room, I'm sure, would be more interested in hearing about the infrastructure. So the benefits of cloud native development actually spans across both domains, right? So infrastructure and applications. There are benefits of running containerized workloads in the infrastructure space. Red Hat focuses on container innovation, and we just introduced with RHEL 8 a set of tools that enable traditional development on your laptop, on your developer's laptop, for the containers. And then through the key registry, you can have the containers developed by your personnel, by your developers, moved into a shared environment, and then you can orchestrate many thousands of them with the cloud-native tools in OpenShift. So final slide, the base image for all you need. This is the true innovative concept that we introduced with RHEL 8. It's called Universal Base Image. That image has no direct ties to Red Hat, but it is also based on Red Hat Enterprise Linux. It's fully distributable for the first time. You can take that image and build your container and ship it anywhere to anybody without having any ties to Red Hat. And there is a support model that comes with it if you decide, or your customers decide at some point, turn the support on. I can talk a little bit more about that if you have any questions. Thank you.
help motivate the question and answer session, I'm going to start off with the question. And Jan, I want to thank you for the update on the merger. This has been an amazing 12 months for the industry in the sense that 6 different companies now have changed ownership in one form or another. And perhaps in our April meeting, we should have a separate panel just on what's life once merged. I think would be fascinating. So what I'd like to do is elaborate a little bit more on the 4th question here, which is, how could you use help from the outside world? Whether it's investors, buyers, governments. But what I'd like to do is to narrow it down to a very specific question, well actually be 2, and that is if somebody, and let me say it could be the government, could be a large buyer, could be a CSP, came to you and asked you from your R&D perspective, the innovations you just talked about, what's the low-hanging fruit? If we gave, and the 2 parts question, part A is, what if we gave you $1 million to either bring it to market faster, make it better, and then the other part is, what if we gave you $10 million? So kind of a small investment or large one. Where do you see kind of that next notch in the schedule or the next piece that you could improve things?
So I think from a schedule standpoint, things are pretty well defined as far as the products that will be introduced over the next few years. I think some of the areas that would be most insightful would be just making sure we have the right priorities, right? As I talked about kind of that last slide, the different coherent technologies that are going to be coming to market over the next few years. Like, say, if anybody has a strong opinion on what the priority of those should be, different technologies that and partners that we should make sure we're collaborating with on those technologies to make sure we bring those like I say co-designed or co-validated products to market at the right time. I think that would be the best insight that we could get from the community here. Like I say, additional investment, I don't know that's going to accelerate things, but like I say, making sure that we stage the technology at the right time is the most insight that we could get from the audience here.
I kind of briefly talked about it at the very, very end. There is one hyperscaler in particular that has jumped on EDSFF. They have a very different mentality of how they want to use it. They're not using it for very dense storage, and yet for the hyperscalers, I think we want dense storage. So literally, they're cutting the density in half. The other thing is they're focusing on one particular capacity, which is driving the vendors to not go for higher capacities. One vendor in particular, I guess I'll name nameless, has pushed out their 32 terabyte drive by a year because they say, oh, no one wants it. And I look at you guys and I go, yes, they do, right? Because when you talk to you guys, when you talk to the DOE and the national labs and stuff, they don't have any problem talking about 50 petabytes. That's no big deal. Or 150 petabytes. That's no big deal, right? But when you talk to these vendors, they go, we don't know anybody that wants a high capacity drive. And I'm like, are you kidding? So what I need from you, what I really need from you is to talk to those vendors that are doing, all of the drive vendors that are doing this and say, guys, I really do want a high capacity, high density drive. I don't want the 18 millimeter version of this drive. I want the 9.5 millimeter version because I want twice the density. And I do want that higher capacity. I want that 32 terabyte drive.
Hey, thanks. Hey, Earl, that wasn't a hypothetical question for Panasas. We had recently that type of funding from a growth VC. And the reason is because, everyone I think knows Panasas. The reputation is that, its reliability and ease of management is well known. And if anything, if you're familiar with the company, it in the past has had its hardware platform designed internally, bespoke hardware. And it kind of fell behind the price performance curve of people like Supermicro and the industry standard components out there. I watched it, I think you all watched it, when Supermicro came out with a new storage platform based on these industry standard components. Instead of us picking that up, putting our software on it, and deploying it into the market to keep up with that pace, we took those same components and designed something internally custom, bespoke, and the results were, because of our volumes, it was very expensive, and we were always a tick-tock behind the industry. And so what's happening now is why we had that investment is now we've ported our software, which everyone acknowledges to be as good as it is, on actually Supermicro hardware, we believe it or not. And so now we have the performance, which I showed, and the price performance because it's based on industry standard stuff. And so our challenge is to provide those proof points because everyone, still has Panasas in mind of being, good but expensive behind the price performance curve, which I showed is like the biggest criteria for high performance computing, ironically. And so it's up to us to go out and to explain that. We were at San Diego Supercomputer Center a few weeks ago, and one of my colleagues during the discussion, one of Ron's colleagues said, one of our criteria is going to be the impact on our storage admin. And we never heard that before from a university because everyone at universities, the saying is that they can just grab a bunch of people to run these things, and that's becoming more and more difficult. And that's again, we talked about that. The criteria of being able to find talent to run these machines is getting harder and harder moving forward. So that's basically what we're doing. We got the money, like you said, and we have to execute now because the people that gave us that money expect us to grow now. So anyway, thanks. I don't even know, but I think it's in that range.
Okay, so what I would want to do would be to take it, what I had talked about earlier, one step further, right? Because right now, we now have all these different layers of storage, right? And we can talk about hard drives and SSDs and form factors, but as we work our way up, right, we've got beyond SSDs, right, we've got node local SSDs, we've got NVMe and M.2 and U.2, and now we have high-speed memory, and we've got things like from Intel Apache Pass, right, to give more capacity, and we've got cache, and now the introduction of high bandwidth memory, right, that is going to be on all of the different CPUs as we look a couple of years out. It's really going to become more and more difficult to do, to better automate work, data flow, right? And how do you get that data? How do you stage that data? What data goes to what level, right? Because there's costs in both dollars as well as in bandwidth and latency, and so trying to figure out how that data flow happens, right, and being able to automate it and being able to make it easier for the programmer, because the programmer and the data scientists, they understand what they want to do with their applications, but maybe don't quite understand the easiest way to implement it when it comes to all this hierarchy, right, from cache all the way out to still tape drives, right? So how do you make it simpler? Right? What is important? Right? We did a nice system with SDSC a number of years ago when I was with APRO, right, which was Gordon. But it's gone a lot further than that now, because now there's even more tiers of storage and data locality, right? So it's really should be about automating and being able to get that data from one place to another a lot easier.
Yeah, so it's somewhat tough to imagine what you can do with $1 million when you operate at a $1 billion scale. We could, yes. But I think, yeah, besides the money, what we need as a community is a little bit more awareness, first of all, in our existence, and second of all, in the interest that HPC has in the future cloud and hybrid cloud environment. I think there is a clear leader right now in terms of where the brains and attention span is. It's in Kubernetes community upstream. It's the second largest community after Linux. So I know it may be foreign to some of you, and you think I'm pitching the product. There is no product for me to pitch. It's the reality of the contributions upstream. So if I would get $1 million, I would go and startup, and I will focus on enabling HPC tools for Kubernetes, because that's going to be a huge market. Many of you will be interested in using or consuming. As a community itself, Kubernetes is aware of the needs of enterprise HPC, and they're pulling in some of the technologies proactively, but scheduling needs a lot of help. Distributed storage is lacking, et cetera, et cetera. You guys have enormous expertise in this room that you can contribute to. If not in money, do it in spirit, because that will preserve this type of environment for the future generations. That's all I'm going to say.
So IBM is very open to partnering. We have a lot of money of our own, as well as we're open to being on the receiving end as well. But IBM already has a very strong hardware and software technology roadmap going out through Power 10, even Power 11 generation, not just for the CPUs, but for all the surrounding I/O architecture, storage, a lot of software teams. So, but if there was a $1 million class project, I think a great place to focus would be on building a team with some other stakeholders to optimize and co-develop software for very, very, very large models. I think climate is its classic one. Someone talked yesterday about climate being like the holy grail or one of the most important use cases. I agree right now. We have the IBM Weather Company working with a lot of the agencies. I personally work with the NASA and DOE accounts on weather. So $1 million would go a long way towards building a team of subject matter experts to work on co-developing these climate model suites for use on the leadership class systems, where you're potentially using the entire Summit or Sierra or El Capitan or whatever system. The $10 million class, I think a great place to focus would be on custom. Appliance is kind of a hard word to use because everybody's still focused on general purpose HPC, but some more custom-ish platforms for maybe inferencing systems or specific industry use cases. We've got so much new technology coming around for hardware that I think you got to get the right people on the team to come up with some really powerful combined hardware and software platforms for some unique workloads, and that's probably like a $10 million class investment right there.
Is coming up what Harry just said, that about the appliance thing. In one of our surveys, we were talking to people in investment banks and asked them, are you open to black box kind of stuff? Are you open to really custom appliance stuff? And the answer pretty consistently was the same. It was, we don't care. We don't care. People can come in and talk about black boxes, custom stuff, as long as our current staff can manage it and we don't have to hire anybody new. Any comment there?
Good point. I mean, I think what we find out with very narrowly defined appliances, the use cases will start to spread out from there, and you'll end up with a general purpose technology even coming out of a black box system.
Sorry, I'll repeat that. So in a lot of the studies we've been doing, Steve and I and the rest of the team, we talked about over the last 2 days that there's a lot of enterprise customers that are now acquiring HPC equipment and HPC technology because they want to move into AI, machine learning, or handle big data, or handle problems that are of a different scale than what they normally are used to doing. And my question then for the panelists, have you seen this at all? And if you have seen it, maybe you can suggest or talk about an example of where you've seen that happening. And let's reverse the order and start with IBM at the end.
Okay, well, what I talked about a few minutes ago was our machine learning accelerator software suite. That was specifically designed to save data scientists a lot of time for faster and better results, but also to get the non-data scientists being able to get their hands dirty doing machine learning. And we had some very quick successes in Wall Street with that. Of course, customers don't like to talk about what they're doing in detail there, but right away we found there was a very a great need for tools to make it easier for data scientists and for non-data scientists to do that kind of work, especially because data scientists are still in very tight demand. I think in private industry they probably jump around even more probably than they do in the government environment, but we kind of met that need with those tools.
I actually agree 100%. We're seeing same interest from verticals, from financial, FSI, telco, etc. But I think where I see the struggle happening right now is actually with OEMs, our traditional friends. And part of it is as the AI and ML workloads are moving out from the corner offices of chief scientists, and they are passing down their work to the IT personnel who needs to deal with it somehow. There is really a kind of a loss of connection between what is the problem that they need to address and what is the solutions that they have available. Somehow we need to help them by educating the IT folks that the AI and ML workloads, nothing but the specialized, slightly specialized hardware that they can manage in the same exact way that they're managing standard hardware. And I see from our OEM connections, working with our OEMs, that this represents a problem to them because they haven't articulated this very well. And so this transition is going to take a couple of years, and folks will get educated. But to me, that's where I think this is the hot kind of point right now, where things need to be addressed. And if you have any ideas on how to help, talk to your friendly OEMs and talk to us as well, because we talk to all of them.
Thanks. So we didn't talk much about what Cray has as far as AI and machine learning, but this is certainly an area that Cray is spending a lot more time in, because we do see it spreading across all of the industries and overlapping, as Steve had mentioned in his talk, with high-performance computing, where we have shared resources, right? And they're running AI on or machine learning jobs on HPC systems, right? So we have a piece of software that helps scalability of these things, because as people have started with single nodes, right, it continues to scale up. And we have parameter optimization tools and things like that. And it really is being used on a lot of the HPC, but it's also for dedicated systems. And we've sold some pretty large ones of those now as people start scaling things up from just a couple of nodes with GPUs, and now they're learning that they can scale these things all the way up to, in some cases, thousands of nodes of GPUs. So it's really interesting to see how the growth of the industry and the growth of just within individual companies, as they start to learn some of the things that they can get done with machine learning that they actually had maybe even done with high-performance computing before.
Okay, thanks, Stephen. That's a good point. And Panasas actually shares that experience a little bit different than your premise. We see, since we're support shared resource HPC facilities, we're getting hit more and more with AI and ML workloads in those HPC classical environments. So they're adding AI to the mix as opposed to creating an AI sandbox somewhere else. And that's what the customers want, and that's the trend that we're seeing. Basically, what Cray is seeing too, with the existing systems being augmented with AI workloads.
So funny because everybody's stealing my answer. But what I'm seeing, not only, I mean, everything GPU, you think with AI, that's an HPC thing, and that's definitely trickling out into the enterprise space a lot. We have our own series of GPU systems that we sell, and what we're finding is those GPU systems are becoming more and more popular. But then what I find interesting is the integration that happens between technologies. So as you can tell, I'm really kind of a storage guy. I didn't used to be when I was at Dell, but now I am now. And NVMe, so what's happening is those GPUs, you get big GPU systems, and what we're seeing is they're saying, but how can I feed those GPU systems? I need better storage technologies to feed those GPU systems. And then you look at the storage systems, and they're like, well, now I need better networking to get access to that, because if I can't get high-speed network in and out of those high-speed drives, then what good are they? So it's the interesting technologies of what's happening now. I remember years ago when we made the transition from 1 gigabit Ethernet to 10 gig, and it just took forever. We thought, 10 gigs is going to happen quick, and we know in our industry nothing happens fast, right? But I think what we're finding is because of the ability of NVMe, because of the ability of GPUs, because of the speeds that we're talking about and the amount of data that we need, I think that transition to 100 gig to 200 gig is going so much faster, and that's happening in the enterprise space now. It's almost comical when I find a customer that says, well, my infrastructure is 10 gig, and I'm like, and you want a whole series of NVMe systems? Are you kidding? You can't. 10 gig is just going to be, that's like sucking through a tiny coffee straw. What are you doing? So I think it's it's all of those different systems, networking, storage, and the compute and the GPU that's requiring more and more capability that used to be an HPC thing that's now, it's in the enterprise.
Yeah, I mean, from our perspective, we've got some of the limitations that some of the other panelists have, that we can't really talk in detail about what our customers are doing, but what I can talk about is some of the things that AMD is doing internally within our IT and other organizations. In the last year or so, we've launched a number of pilot programs around AI and machine learning, around supply chain operations, as well as our engineering workflows to, like I said, look at opportunities for AI assisted or machine learning assisted acceleration to those processes. And I think the things that we're going to learn from these pilot programs, we'll be able to share with our customers over the next 6, 12, 18 months, and try to share some of those best practices throughout our industry collaborators.
Great, thanks. And any questions from the audience?
One more. HPC's been doing some things with edge computing for years, power grid management and various things, but it's definitely ramping up, and there's a lot of expectation, at least from what people tell us, that HPC is going to turn out to be pretty important at the edge. What are you guys seeing or doing about HPC edge computing?
Here at one of the instruments, so it's collecting the data at quote-unquote the edge, and then that data gets pushed over to the big machines here. So I think you'll see more and more of that as the instruments are creating all this data, there needs to be something catching it and then doing some processing on it, and then it gets pushed over to the big facility here to do even more number crunching. Because we were here actually trying to find where the Panasas was on site, and we went here first, and they said, oh no, it's over at one of the big data collection sites.
Any other response?
Yeah, I think one of the things that Cray is seeing is a lot more of the data ingest, right? Whether it's from electron microscopes or telescopes or whatever may be out there that's collecting all of this data that they now want to crunch. One of the nice things about Slingshot that Steve Scott was talking about yesterday is it's Ethernet compatible, right? So now you can actually attach a lot of that same instrumentation directly into the same network with the storage, with the compute, right? And we're seeing a lot of interest in customers in being able to bring all that together with a single unified fabric.
And maybe I'm going to grab the mic first.
Sure. Two things IBM is doing for HPC at the edge. One is that we're coming up with inference systems for use out in the field based on a different level of GPU than you would have like in a V100 in a leadership class system. Another thing is working with FPGA vendors and some of the other startups in Silicon Valley on the custom silicon for more edge type HPC AI devices or systems.
Yeah, All I wanted to add, actually, in a similar line to what Harry was saying, I mean, there is a duality in the definition of what Edge HPC is, right? Is it a highly distributed system that is highly scalable, or is it the HPC tasks that you now need to run at the edge?
Edge.
Okay, well, so that's your view of that differs from many others, right? Right. Well, what we're seeing people starting to push is more along the lines of moving AI and ML workloads, or actually doing some inference and processing right at the edge. So lightweight devices, but very highly capable, able to bring just the essence of the data ingest that they're having, like I'm leveraging everybody's comments from before, right? Right at the edge, and only doing a minimal send upstream, right? So this is truly a distributed system. But from our perspective of a software vendor, the fundamental challenge in either scenario is management. How do you manage this instances? How you manage these disconnected instances? And because we focused so over-focused on the containers and Kubernetes, we're actually working on disconnected management nodes, combination of master and worker nodes combined on a single node, et cetera, et cetera. So there's a lot of techniques that need to be employed in order to effectively manage this distributed cluster of things, whether it's part of one big thing, just physically distributed, or it's actually tiny little things that doing their own task, running their own task, but still have to report back to the next echelon. So
Great. So I think we have just 1 minute left, so if you can make it quick.
I will make it quick. We have, at Supermicro, one of the things that we're finding, and this is not exactly going where you're going, but one of the challenges from an engineering standpoint is you put boxes, you put things out on the very, very edge. You may not have power. You may not have cooling. You may not have a lot of things. So now I need to have things like a fanless design. How do I do that? Integrating FPGAs so that I can have FPGA computing. The other thing is we're all looking forward to 5G so that I may not have a wire that actually goes there, right? So I need to go wireless, and we're hoping that 5G is really going to help that. But then the next thing that we're also embedding in our solutions are things like encryption, because if I'm going to send that wirelessly across, I probably need to encrypt it, because I don't think I really want that to just be caught, you know, and used. So encryption and compression, if I have a whole bunch of data on the edge, how do I get it in? How do I get it there if I've got a limited bandwidth on wireless? So encryption, compression, these are things that we're integrating, and we already have integrated in our edge computing. We've been doing embedded computings for MRIs for years, right? So we've got those kind of things, and we're used to that kind of putting an embedded solution someplace in a box somewhere, but now we're talking about putting it in somebody's field, right? And so it's a very different kind of mode where you've got to make it small, tight, and use very little power.
From an AMD standpoint, we look at the edge market from our embedded product line, and one of the great things about that product line is they get to pull from all of the innovation across everything that AMD does. So the scenario you talked about at kind of the end, the very high performance edge device, where they could pull from all of our data center products there. If there's a need for a fanless edge device, we've got some of our laptop parts and very low power parts. So across that full spectrum, from fanless up to data center class equipment at the edge, they can pull from that portfolio, but also connect it with high performance, high speed, low latency I/O, right? With the PCI Express Gen 4 that we've got across the portfolio, whatever power profile you want to have at the edge, you can still have the good connectivity to it across that portfolio.
Great. So I'd like to thank our panelists for taking the time.